Whoops. Not full screen. You can't see it. Okay. So let's continue on with our talk about objects in Java with inheritance or reusing the interface. By itself, the idea of an object is a convenient tool. It allows you to package data and functionality together by concept. So you can represent an appropriate problem space idea rather than being forced to use the idioms of the underlying machine. These concepts are expressed as fundamental units in programming language by using the class keyword. It seems a pity, however, to go to all the trouble to create a class and then be forced to create a brand new one that might have similar functionality. It's nicer if we can take the existing class, clone it, and then make additions and modifications to the clone. This is effectively what you get with inheritance. With the exception that if the original class, called the base class or superclass or parent class, is changed, the modified clone, called the derived class or inherited class or subclass or child class, also reflects those changes. Okay, so guys, this paragraph highlights a real problem in studying computer science. Okay, unlike some other fields of study that are kind of monolithic, right? Like you have this kind of set of universities, they all kind of agree on the same thing. They all kind of they're like a cabal of like thinking, right? Okay, like for example, you have to agree that Shakespeare is a great writer in order to be considered a great English professor, right? You can't go in and go, do you guys see where I'm headed with this? Like, in many other subject areas, you have to agree, you have to subscribe to a common something in order to be taken seriously. Because it's science, like it originated as professional, like, I don't know, it's just over time that's what is developed, right? Like they all subscribe to a common vocabulary. Computing, on the other hand, is a very young science, right? So you have a lot of people working simultaneously on the same things, and it creates this situation. And in addition, most people that have done computing in the past, it hasn't necessarily been like a formal area of study starting out. So what you have still in computing, which I think will eventually iron itself out, is you have this like just a lot of duplicate vocabulary, okay? So, and it can get really confusing because you might read 3 different articles. Like say you listen to one tutorial and they call it a base class, and you go somewhere else and read something and they refer to a super class, and then you go somewhere else and they call it a parent class, right? Well, unless somebody relates that, you need like a Rosetta Stone of programming, right? So it's good for us right now to write in our notes that these terms are equivalent, okay? Okay, so the original class is also called the base class, superclass, or parent class. Let's go ahead and write that. An original class is also called the base class or superclass or parent class. Okay. So that is the idea of inheritance. So now let's write down a definition of inheritance. Okay? Inheritance is to clone a base class and then make additions and modifications to the clone. So you copy the base class and then you make additions and modifications to the clone. Okay. The next part of inheritance, though, so you clone a base class and make additions and modifications to the clone. period. If the base class is changed, those changes are reflected in the clone. You guys get that? Okay, so it's like if you had a pattern and you make copies using the pattern, but if you change the original pattern, all the copies you've made also change. Is that kind of a weird thing to think about? It's like if you had a cookie cutter and you were cutting out like Christmas trees, right? And all of a sudden you put an ornament on the cookie cutter, and all the cookies you had cut out also all of a sudden had that same ornament. Okay, do you guys see what I'm saying? Okay, if you had a cookie cutter that was a reindeer with 2 horns, and you cut a bunch of cookies that all had 2 horns, and then you added a 3rd horn to the cookie cutter, all of a sudden all the cookies you had previously cut out now have 3 horns. You guys understand that? Okay, so it remains connected to the base class. So although we're saying it's like a clone, it's not a clone like Dolly the sheep is a clone, right? It's a clone as in it's a copy, but if I change the base class, those changes are reflected in the clone. Okay? That's inheritance. So I don't know if clone is really the best analogy, right? Okay? It's like you're taking a class and you're adding to it or changing it in some way, but it remains connected to the base class. Okay? Okay. So while we are all about the base class, we're also all about the derived class. I guess you could say that. Okay? Okay. Okay, so now let's write down, so you guys should have now in your notes that the original class can be called like 3 different things, right? Base class, superclass, or parent class. You should also have a good solid definition for inheritance, okay, written down. And the modified clone, so now we're going to write down a good definition for the derived class. Okay, so the cloned class, also called the derived class or inherited class or subclass or child class. Okay, so you do actually need to know all of those synonyms. They all mean the same thing, but each one of those is widely used. Okay, you'll see these all the time. The child class, the subclass. I'd say the derived sub, usually superclass and subclass are the ones that are generally used. Okay, in general, if somebody talks about objects, they're going to talk about a superclass and a subclass. That's what I've seen mostly. Or a base class and a subclass. Or a parent class and a child. Usually parent and child is what I'm talking about. But you could see any of those words. Okay. The arrow in this UML diagram points from the derived class to the base class. As you will see, there is commonly more than one derived class. A type does more than describe the constraints on a set of objects. It also has a relationship with other types. 2 types can have characteristics and behaviors in common, but one type may contain more characteristics than another, and may also handle more messages, or handle them differently. Inheritance expresses this similarity between types by using the concept of base types and derived types. A base type contains all the characteristics and behaviors that are shared among the types derived from it. You can create a base type to represent the core of your ideas about some objects in your system. From the base type, you derive other types to express the different ways that this core can be realized. Okay, you don't need to write anything down there. He's going to go into a good solid example here. For example, a trash recycling machine sorts pieces of trash. The base type is trash. Okay, so we are imagining that we have this machine that sorts trash, right? Each type of trash has a weight, a value, and so on, and can be shredded, melted, or decomposed. Okay, so we have a base class, we're calling it trash. Okay, the characteristics are weight, value, and he's saying some others. Okay, the methods, like the public methods, the interface include shredded, melted, or decomposed. Okay, So trash is our base class, right? Our base type. And then he's even using type and class interchangeably, right? All right. From this, more specific types of trash are derived that may have additional characteristics. A bottle has a color or behaviors. An aluminum can may be crushed. A steel can is magnetic. In addition, some behaviors may be different. The value of paper depends on its type and condition. Using inheritance, you can build a type hierarchy that expresses the problem you're trying to solve in terms of its types. Okay, let's talk about why this is a good idea, why it saves you time in the end. Okay, so by making this base class of trash, okay, and then we would make other types of data based upon what type of trash it is. What we get is the ability to add characteristics to every type of data by adding it in one place. Do you guys see that? So let's say you had a code that was like 500 pages long. You had 50 different types of trash, but they're all derived from this single base class. Let's say you had to add a characteristic like let's say you hadn't put in weight, and all of a sudden you have to have weight in all of your objects, right? In all of your different types of trash. Then what you can do is you can just change that base class in one place, and you get that characteristic everywhere else. Okay, so it's not just like it helps us in that it makes sense to represent things as they are in the real world, but it also makes sense because it's a time saver. Okay, in the end, most things in programming that are advances are really advances in ways to be more efficient in programming. All right, so that's one more advantage of why you would use this class structure and why you need to think about this class structure, because it can affect the way that you can change things later on. All right. Okay. A second example is the classic shape example. My favorite. Perhaps used in a computer-aided design system or a game simulation. This type is shape, and each shape has a size, a color, a position, and so on. Each shape can be drawn, erased, moved, colored. Notice that he's giving us characteristics and public methods, right? So that's the basics of every object, right? And as an example, he gives us just that. Characteristics, methods you can call, right? Okay. From this, specific types of shapes are derived or inherited. Circle, square, triangle, and so on. Each of which may have additional characteristics and behaviors. Certain shapes can be flipped, for example. Some behaviors may be different, such as when you want to calculate the area of a shape. The type hierarchy embodies both the similarities and differences between shapes. Okay? So the things that are common among all shapes would be collected into this shape base class, right? Things that are different for every shape would be collected into these derived classes. And it could get more complicated. For example, you might have a rectangle class derived from shape and a square class derived from rectangle, right? Okay, something like that. Or quadrilateral class derived from shape, and then all your quadrilaterals are derived from the quadrilateral class, right? So it just depends on the particular situation, all right? In general, you would arrive at this, in my experience, you would arrive at this base class based upon your initial set of derived classes. So you would know that, like, some of the derived classes you want to make, and you would collect those commonalities and make a base class that's useful to you, okay? So this idea of inheritance, not used all the time, all right? It's used when it's useful, all right? Because remember, we're always going to go back to this. Programming is utilitarian. You don't do things just because you do them. There is no tradition. There is no, we do it because we do it. That's wrong, okay? That's a wrong reason to do something in programming. All right, we do it because it's useful. We do it because it makes our work easier. We do it because it makes our work better, okay? Those are the only reasons to do something in programming, all right? Okay. Which is different from some other subjects, which is why I love programming. Okay. So Forecasting the solution in the same terms as the problem is tremendously beneficial because you don't need a lot of intermediate models to get from a description of the problem to a description of the solution. With objects, the type hierarchy is the primary model. So you go directly from the description of the system in the real world to the description of the system in code. Indeed, one of the difficulties people have with object-oriented design is that it's too simple to get from beginning to end. A mind trained to look for complex solutions can initially be stumped by its simplicity. Okay, guys, I'd like you to go ahead and draw this diagram in your notes. Okay, so just draw it exactly as shown here with shape, draw, erase, move, get color, set color. And then the circle, square, triangle with the arrow going up. And go ahead and write base class or parent class, whatever your favorite synonym is for base class, okay? And then your derived class, write derived class down here, just so you remember, just to relate it back to those vocabulary words that you just wrote. Okay, so base class next to shape, derived class, child class, subclass, whatever you want to write, whatever synonym you want to write next to the derived classes down here is fine. Okay? As you're doing that, let me tell you something I've always had difficulty with. When you make a circle class, you would have to choose. It's a rigid hierarchy, right? Okay, so you can't make a circle class derived from two different classes. You have to choose one class that it's derived from, right? Okay, you can include other classes inside of it, but the inheritance needs to come from one class, right? You can't inherit both. But we'll see if there's a solution to that situation later on. Okay, everybody got it done? All right, awesome. Okay. When you inherit from an existing type, you create a new type. This new type contains not only all the members of the existing type, although the private ones are hidden away and inaccessible, but more importantly, it duplicates the interface of the base class. That is, all the messages you can send to objects of the base class, you can also send to objects of the derived class. Since we know that the type of a class, since we know the type of a class by the messages we can send to it, this means that the derived class is the same type as the base class. In the previous example, a circle is a shape. This type equivalence via inheritance is one of the fundamental gateways in understanding the meaning of object-oriented programming. Since both the base class and derived class have the same fundamental interface, there must be some implementation to go along with that interface. That is, there must be some code to execute when an object receives a particular message. If you simply inherit a class and don't do anything else, the methods from the base class interface come right along into the derived class. That means objects of the derived class have not only the same type, they also have the same behavior, which isn't particularly interesting. I have no idea what he's getting at in that paragraph. Okay? It sounds to me like he's saying if you just make a new object that inherited a base class, you make a derived class that is identical to the base class, why do it? Because you still just have the base class under a different name. That seems to me like what he's saying. Okay, I'm not sure. Okay. You have two ways to differentiate your new derived class from the original base class. So that indeed was what he's saying. Basically, he's saying, why would you derive a class? Like, why would you make a circle class derived from a base class called shape if you weren't going to change it? You would just use the shape class, right? Which seems weird because why would you? It wouldn't necessitate making a derived class unless you wanted to change it. So, excuse me. The first is quite straightforward. You simply add brand new methods to the derived class. These new methods are not part of the base class interface. This means that the base class simply didn't do as much as you wanted to, so you're adding more methods. This simple and primitive use of inheritance is, at times, the perfect solution to your problem. However, you should look closely for the possibility that your base class might also need these additional methods. This process of discovery and iteration of your design happens regularly in object-oriented programming. Okay, I love the word iteration, by the way. Okay, that is the way to get to good code. It's going back over it and over and over it, changing it a little bit, little by little your code gets better. Okay, all right, so he's saying that one way to change a derived class from a base class is that you basically just add more methods to it. So it just does more stuff, right? Okay, but he's also saying that if you need to add those methods to your derived class, you might want to be careful because it suggests that you probably need those methods in your base class as well. Okay, so just adding new methods can be a clue that your base class is incomplete and you might need to just add methods to your base class to begin with. Okay, so that's like a clue. If that starts to happen, you say, hey, maybe my base class really needs to get changed. Why would you want to do that? Let's say you make 87 different kinds of light bulb classes with all having the same method called turn on. Well, guess what? You shouldn't have written that 87 times. You should have just added it to your base class to begin with, right? So you're really looking for situations early on can save you time, because when you add something to your base class, it just is automatically kind of, you get that with it, right? It just kind of comes with that method when you make a derived class, right? Okay. Shape. Okay, so here's an example of that. All right, so shape has draw, erase, move, get color, set color. Okay, circle, square, and triangle are the derived classes, and now we're adding flip vertical and flip horizontal to triangle. Okay, now obviously square and circle don't really need those two methods in this case, right? Why would you flip a circle horizontally or vertically? You wouldn't be able to tell the difference, right? Okay, same goes with a square. They'd be identical, right? It doesn't matter if you flip it horizontally or vertically, unless you set the center. Well, anyway. Okay, so I think that's his point here. All right. But other types of shapes might need that, right? So many other types of shapes might need those two methods. So that, in my opinion, from his drawing here, that to me, once I get to triangle, all of a sudden I had this third derived class triangle. All of a sudden I go, wow, I need flip, vertical, and horizontal. I should think to myself, hey, wait a second. Once I make any shape that doesn't have symmetry, I'm going to need flip to horizontal and vertical. Maybe I should go ahead and put that in the base class, and then when I don't need it, it just kind of comes with it, and I wouldn't use it anyways, right? For a circle or anything with symmetry, right? So, anyway, I digress. Okay. Although inheritance may sometimes imply, especially in Java, where the keyword for inheritance is extends, that you are going to add new methods to the interface, that's not necessarily true. Okay. So, let me read that again, and let's go ahead and write that sentence down. Although inheritance and its keyword extends, okay, you guys writing that? Although inheritance and its keyword extends implies adding new methods this is not always true. Although inheritance and its keyword extends implies adding new methods, this is not always true. Alright guys, we're like 66% of the way through. You guys are doing great. Okay, just hang in there. Alright? I can feel it's getting more interesting, isn't it? Okay, the first couple lectures were confusing. Now you're like, oh, that's awesome. I wish you would read to me more. Wow, really? I can't believe it. I'm so interested when I read. All right, okay, let's move on. Okay, the second and more important way to differentiate your new class is to change the behavior of an existing base class method. This is referred to as overriding the method. Okay. So let's go ahead and write that down. To change the behavior of an existing base class method is to override that method. To change the behavior of an existing base class method is to override that method. Once again, to change the behavior of an existing base class method is referred to as overriding that method. Okay, so here we see an example of that. Guys, after that note, let's go ahead and draw this picture right here. Okay. Thank you. Real quick, super quick, take 2 seconds. Okay, in your notes. Size is up to you. You can draw it small, you can draw it big. You don't even have to do triangle. You can just do circle and square. But there need to be 2 derived classes on your notes, so that you get that it's a one-to-many relationship, right? Okay. To override a method, you simply create a new definition for the method in the derived class. You're saying, I'm using the same interface method here, but I want to do something different for my new type. Okay, so it's very straightforward. Basically, you just write a method with the same name, and you use a keyword to notify the programming language that you are changing, right? Okay. All right. Everybody ready? You're telling the derived class, you're telling the class that you're making a new method and they should let it go. They should let it go. You're saying let it go. You're welcome for that. You're welcome that you now have frozen in your head for the rest of it. Okay. All right. So that is overriding. Okay, so to summarize this section, guys, the idea here is that to keep things simple, you don't want to just go putting in new classes just willy-nilly all over the place. Okay? You don't want to just start adding things everywhere. It's easier in a lot of cases to just start adding things right where you need them, rather than thinking through the structure of your objects and making sure that if you're able to put something in your base class and then override it in your derived classes, that in the long term is a better solution. Okay, if you just start adding things in, you want less methods overall. That's the idea. If there are less methods overall, or if those methods are derived or are overridden in the base classes when they need, or overridden the derived classes when they need to be, but not when they don't need to be, that your code will be more simple, which translates into more maintainable, which translates into less expensive. Okay, that's the idea. Is a versus is like a relationship. There is a certain debate that can occur about inheritance. Should inheritance override only base class methods and not add new methods that aren't in the base class? This would mean that the derived type is exactly the same type as the base class, since it has exactly the same interface. As a result, you can exactly substitute an object for the derived class for an object of the base class. This can be thought of as pure substitution. It's often referred to as the substitution principle. In a sense, this is the ideal way to treat inheritance. We often refer to the relationship between base class and derived class in this case as an is-a relationship, because you can say a circle is a shape. A test for inheritance is to determine whether you can state the is-a relationship about the classes and have it make sense. Okay, everybody understands that, right? Okay, when they say the interface is the same, that basically they're saying that you have this shape base class, and if we're talking about pure substitution, that basically every method is identical. The names of the methods are identical, so the interface is identical, right? So in circle, draw, there's a draw, erase, move, get color, set color, and those methods are all present in circle, but they've been overridden and do different things. You guys understand that? So while draw, if you say draw a circle, it's obviously going to be different code than draw a square, right? But the method itself, the name for the method, is present in the base class, so the interface is the same. But the underlying code is then overwritten for every derived class. That's what they're talking about with pure inheritance, pure substitution. Okay. This doesn't seem real to me, realistic to me in a real life situation. Okay, I understand it as a idea, like a great thing to do if you had all the time in the world to like be designing objects. In reality, this would be very difficult to accomplish in a real actual system. Okay, but it's an ideal, right? Okay, there are times when you must add new interface elements to derived type, thus extending the interface and creating a new type. The new type can still be substituted for the base type, but the substitution isn't perfect because your new methods are not accessible from the base type. This can be described as an is-like a relationship. That's this author's term. I doubt you'll hear it anywhere else. The new type has the interface of the old type, but also contains other methods, so you can't really say it's exactly the same. For example, consider an air conditioner. Suppose your house is wired with all the controls for cooling. That is, it has an interface that allows you to control cooling. Imagine that the air conditioner breaks down and you replace it with a heat pump, which can both heat and cool. The heat pump is like an air conditioner, but it can do more because the control system of your house is designed only to control cooling. It is restricted to communicate with the cooling part of the new object. The interface of the new object has been extended, and the existing system doesn't know about anything except the original interface. Okay. This is dangerously close to this author's opinion. Okay, so you don't need to write this part down. All right, I get his opinion. Okay, so he's saying that like he's basically saying that, well, you understood what he said. Okay, he's saying that derived classes should be in the same type and that they should have identical interfaces when possible. Maybe I'm not understanding exactly his point. It doesn't seem to me to be that big of a deal myself, but I guess there could be a case for maintenance of code where that's possible. Okay. All right. Of course, once you see this design, it becomes clear that the base class cooling system is not general enough and should be renamed to temperature control system so that it can also include heating, at which point the substitution principle will work. However, this diagram is an example of what can happen with design in the real world. Okay, that's true. All right, so I get his point. Basically, he's saying that, oh, that's interesting. So his point is not that you should rewrite derived classes. It's that the base classes themselves should be rewritten to incorporate new functionality. Okay, so basically you should rewrite as high up the chain as possible or reflect those changes into your base class. Okay, so that's his point, which is a good point. Okay, I'm not sure when you're actually coding, sometimes time gets in the way. So it's probably a good idea, but not always realistic. If you were asked to design a system, though, like on a test, you would want to make the point that you were reflecting that you were going for this substitution principle. Okay, so if somebody asked you on a test, hey, what's the problem with this object? You might say, okay, well, the derived class has a lot of methods that aren't reflected in the base class. Or there are a lot of duplicate methods in derived classes that should be reflected in the base class. Okay, that's a valid point, all right? Where somebody hasn't used the base class effectively to reduce the amount of code in the derived classes, right? Okay. When you see the substitution principle, it's easy to feel like this approach, pure substitution, is the only way to do things. I don't see it that way. And in fact, it is nice if your design works out that way. It is nice. But you'll find that there are times when it's equally clear that you must add new methods to the interface of a derived class. With inspection, both cases should be reasonably obvious. Okay, that last part, guys, this part, the idea that you should basically, we're going to call that bubbling up, that basically these changes to the derived classes should bubble up into the base class, okay? Like if you have a new derived class with new functionality, that the base class should then reflect that new functionality. Yeah, that's nice to have. It's hard to make general statements about coding like that. In general, you want to have a lot of kind of simple standards for coding that create maintainable code. You don't want to put a lot of restrictions on how people are forming their data. Okay, that's my opinion. Just like the author has his opinion, that's my opinion. All right. Okay, guys, that is it for today. I would like to congratulate you on getting through this very lengthy lecture from a very boring reader. And we are one step closer. We are one half of the way done with our Java object lectures. Let's give ourselves a round of applause, guys. That was awesome and enthusiastic. Thank you.